Okay, let's get started. So, any question from last time? Let's start with a quick review as always. So last time we go over this very technical proof of lower bound for the search problem, which proved that Grover's algorithm is optimal. So once again, the idea is that we think our algorithm very generally has some is interleaving between our oracles called those OF and some very complicated unitary, but that doesn't depend on oracle codes. So algorithm goes is UO, 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 UO. And what we check is how the quantum state of the algorithm evolve through this computation and how this evolve when we comparing between different. So when we compare how this oracle, when we compare like those trajectories for different f. So we have this mental picture. So we have this Hilbert space where the algorithm starts somewhere. So this is starting point that doesn't depend on f. So for whatever f, the starting point is the same. And as the algorithm evolve, different input, so different small f, will give different trajectory on the Hilbert space. And the first key point here is that those u doesn't depend on f, and so they don't change the distance between these different trajectories. And the other thing, important thing is at the end, those trajectories need to have some kind of separation to make sure that the yes instance f has a good accept probability and the no instance f has a better accept probability. So there is this kind of binary separation that separate the yes instance and the no instance. So yes instance should all separate to this half, and the no instance should all separate into the other half. And then we go to more specific about our decision version of Grover. So we want to check some pairs of yes and some pair of no. And it's here, right? So we think, so this depends on problem and require you to be smart about your problem to solve about. But for this decision version of Grover search, we think the O0 input and those input that has a 1 somewhere are pretty hard to distinguish. And so we will check our progress function, which is sum of all pair of those distance. And the distance we use is just the state, the state. So once again, the state, we're thinking about the state that is the state of the algorithm that get evolved through the course. Yeah, so this state, and we're thinking about how it evolves when your input is O0, and compared to how it evolves when the input has a 1 somewhere. And we sum over all the possible location of the 1. So we go to this more specific slide. Oh, yeah. So this is a progress function. And so the psi k is the state of algorithm when the input is O0. And because there is only one O0, so we just didn't write it anymore in this notation. And the psi sk is the, okay, so we can compare. So the psi k compared to the state of the algorithm when input is this O0, and this psi sk, okay, and this psi sk is the state of algorithm when the 1 is at the x location. Okay, so we are summing over this distance, which is just this is vector difference. So we take the difference of those two vectors, then have non-square, then we sum over all possible x location, which is or the location of this one. Okay, so this is a progress function we sum over, and we say that we need to sum over all those because if you just consider a specific pair, then it's very easy to distinguish even for classical algorithm. Say if you are trying to distinguish the O0 string and the 0, 1, 0, 0, 0, then you just query the second location and you should be able to distinguish those f and f prime. But if you are sum over or basically average over all possible x location, then it's pretty hard to distinguish it. And you can kind of see that in our calculation. So it's in this step. So we kind of do this very smart hybrid to break our difference into two parts. And the second part, which we call C, we have this psi k inner product with x, right? And so you see this is basically like which x you want to create for your psi k. So remember, psi k is the audio string. So this will basically determine whether you want to check which location of your audio string. And you see that, so if this is x, so if psi k is at say 1, then let's say 0, okay. So if your psi k equal to 0, right? If your psi k, use this. Excuse me. How do pen. Okay. Yeah. So if your psi k equal to say 0, then that corresponding to you are querying the 0's location, and you will be able to distinguish between the audio string and the 1000 string. Okay. And yeah, I think you should be able to see that here. Kind of, yeah. If your psi k is 0, then you are going to be able to get something from this O0, right? This OX minus I. And yeah. Yeah. And here you see, but you see that if you put your psi k equal 0, then that only distinguishes between this O0 string and this 1000 string, and it gives you no distinguishment to other string. And but you also have the restriction that, well, the psi k has like a bounded norm. So all this weight need to sum over into something. So you can only get the bounded progress when you averaging over all the distance between different pairs. And well, then we do everything actually rigorously with the math. So wait, this is okay. Yeah. Okay. Wait. Okay. If I erase and erase. Okay. Anyway, so we do everything rigorously, and then we found out that the C term is bounded. We found out this C term is bounded, and the progress with each step, which is dk plus 1 minus dk, goes like square root of dk, and then from here you can calculate that dk goes. From here you can calculate that dk goes like k squared, and we skip over the calculation and just use the induction to show that this indeed will make the dk is smaller than this 4k squared. Okay. So we show that this progress can at the most grow quadratically, and we also prove that at the end of the algorithm, the total progress need to be at least omega big N. That is because we are summing over big N different pairs. And each pair need to be at least constant different distance. And this is where we expand out to a lot of different approach. So we start with many classes ago we argued with intuitively, if you have a constant probability to distinguish two states, then there should be probably constant distance away. And here we give I believe 4 different proofs. So the first proof is a very crude bound. So you go through algebraically and say that if you have a really large gap, then those two states need to have some constant distance, about 2/3 here. And we say that this is kind of a beta bound, and we actually know the optimal bound. So the optimal bound is that if at the end of your algorithm you accept or reject with probability 1 minus epsilon, then the inner product between your two end states, let's see here, let's use this again. So if you are saying, so you accept yes instance with 1 minus epsilon probability and at least 1 minus epsilon probability, and you accept no instance with at most epsilon probability, then whatever state here and whatever state here, their inner product cannot be too big. Okay. And then you can translate inner product to all these difference pretty easily. But anyway, the inner product upper bound will be the 2 square root epsilon times 1 minus epsilon. And let's do a sanity check once again. So if epsilon equals to 0, then this is 0. So that's kind of expected. Right. So if epsilon equals 0, that means that you are distinguishing yes case and no case perfectly. And then that means your state needs to be orthogonal. And if epsilon equal to say 1/2, then basically you are doing no distinguishment. So you are because it's half probability and half probability, so you have no distinguishment, and this should be a trivial upper bound, and indeed that's 2 square root 1/4, and thus this bound become 1, so you have no bound on inner product at all. Okay, and it's actually tight bound. Can kind of see from one of our proof. Anyway, so this is a bound, and we show that if you pick epsilon equal to 1/3, then you get some positive constant bound here, and so that's good. And we went through 3 different ways to prove this. The first one is just doing this algebraic bound better. So yeah. So it's you inserting this identity equal to p plus 1 minus p, but you also notice that p and 1 minus p are both projectors, so they are equal to their squares. Then you group these through things, then use lots of Cauchy draws carefully, and finally that you found this is true. And the second way actually also kind of prove that our bound is optimal. So you think about so we only have 2 states A and B we are trying to distinguish. Then we think that the optimal way to distinguish them is probably a very symmetric way. So this one is not quite rigorous. But anyway, so we only think about this 2-dimensional space because intuitively other dimension should not matter. So in 2 dimension, you try to distinguish those 2 vectors. And the best way is probably this 0 and 1, which corresponding to P and 1 minus P, like this way. Then you do trigonometry and then you find out that you place things like that. Then let's see, the error probability will be sine squared is delta angle, and you do all the sine cosine, and you find out their inner product will be about the sine times cosine will be about square root epsilon 1 minus delta epsilon times 2. Okay. And yeah, and I think these also prove automatability because you show that well, maybe not quite, but anyway. So this is another proof. And finally, there's a proof 3, which uses the information theory. We don't quite teach in this class, but this is quite nice intro to show you that what the quantum information theory can do. So we introduce two quantities that are pretty useful. They are they are distance measure between two quantum states. And well, for pure state is a bit boring, but so usually it's used to track the difference between density matrices. And anyway, so there are trace distance and fidelity. And if you study like theory, information theory, classical information theory about distinguishing distributions, so distribution 1, distribution 2, and so those two are actually classic generalization of classical distance measure between two distributions. So trace distance is a generalization of total variational distance, and fidelity is a generalization of classical fidelity. So it's nice thing to know if you already know those two classical things. And maybe total variational distance can be interesting. So total variational distance is that you have distribution 1 and distribution 2. Distribution 1 and distribution 2. And so the classical total variational distance is just you take a difference between those two distributions. So you think they are like vectors, so you can take a difference. Now this difference has like plus and negative, but anyway you take the absolute value, and well then you take a trace, but it's not quite trace, you sum over all the coordinate, and 1 over 2. So that's the total variational distance. So you see that if those two distributions has a different support, then when you, right? So if it is D1 and it is D2, and then you take a difference and then it becomes this positive, negative, but you take, but then you take absolute value, so it becomes positive again, and you sum over everything, it should be 2, then divided by 2 is 1. Okay? So if your distribution has no overlap, then the difference is 1. And if you have total overlap, obviously the distance, the difference is 0, and so this is 0. So there is some quantity from 0 and 1. And you generalize this to quantum, then instead of the difference between the distributions, you have this distance between density matrices. Okay? So you have the density matrix of the first state and the density matrix of second state. You take difference and the absolute value, then trace, then divide by 2. Okay? So that's trace distance. And we use this property that it has, I should probably, well, anyway. So we use the fact that it is a very operational interpretation. So it's a tight upper bound. We don't need a tight, but anyway, it's an upper bound on the distinguished probability of those two states. And that means that if you do any measurement to those two states, and for example, a binary measurement, then its bias will be at most this trace distance t. And so we write bias in terms of our language. So we say we do two measurements, and the acceptance probability will be 1 minus epsilon and epsilon. So the difference will be upper bounded by this t. T basically says what's the distinction probability between those two states. And so the other information measurement is this fidelity, which is very hard to define for density matrix, but for pure state, it's just inner product, the thing we have been calculating. Okay? So fidelity is pure inner product, and trace distance is the measurement distinction probability. And so we want the relationship. So this is basically the starting point, is the end point we want. And for pure state, there is also a very nice relationship to just connect these two quantities. So we know fidelity squared plus trace distance squared equals to 1. And so basically you just use those three things and they give our results. So starting with, we go, so we go the other way, but however, we can starting with trace distance and calculate the fidelity, and we get a bound on the fidelity. Okay. We try to go the other way, so we start with the fidelity, then we write it in terms of trace distance, and then in terms of this epsilon. Okay. So this is quite a long review of the lower bound we did. Any question? If not, okay. So let's theorize. If not, so let's actually start talking about something new. And change to the new slide. So let's talk about a bit more. Let's theorize the Grover's algorithm a little bit, and we're talking about using it like a sub-algorithm to design more complicated quantum algorithms. Okay. So let's first talk about what Grover's algorithm is, the OR function. We have mentioned this a bit before. And this is just really changing our view a little bit. And so remember we have been talking about our query algorithm, like a big F on small f. Right? So there are like two inputs, because we have this big F function on a small f function, and a small f is like a function on small. Small f is like a binary function on small and b string to 0, 1. And so now we are just changing this small f to like a x that's a big and big function. Okay. Because we don't really care about the structure of this small f too much. And so we just, and we have been talking about, we can just looking at the truth table of small f, and it's a big and big string, right? And so we are just making this more explicit. So instead of big F of small f, now we just talk about big F of some x, which once again x is a big and big string. That's just the truth table of small f. Okay, so and we just think it is x1, x2 to x big N. I guess we are also changing counting, so instead of 0 to n minus 1, we change counting 1 to n. Okay. Shouldn't be too confusing, because starting from here will be a bit less rigorous and talking things in more high level. Okay. But anyway, so we change. We are doing nothing. We are just changing notation. So from small f to x. Okay. And now we think about what is this decision version of search on x. Okay. And basically we are determining whether we are trying to see whether those f. So in terms of small f, we are seeing is there any mark item, and instead of x, it's just whether there is any xi equal to 1, right? So once again, this is just changing our notation or viewpoint. And what's the function that computes whether a string has a 1 somewhere? Well, that's just an OR function, right? So if you are just OR over all those bits, so the x1 is 2 to xn, x beacon, this 1 bit, right? Because small f was a binary function. And yeah, so you just OR them together. So this is a beacon bit OR. I can say beacon here. If this is O0, then the OR is 0. And if there is any 1 here, then when you OR through everything, it should be 1, right? Okay. And yeah, so that's why we say the Gover's algorithm or the decision version of the search function is the OR function. Because if you think about this truth table as a big and big string, then trying to search there is a 1 is equal to compute the OR of all those bits. Okay? So that's the OR function, and we are going to talk about more function, other different function on this big and big string x. Okay? And okay, so now we think about the complexity of those OR function. And well, we're basically just restating our results. And so what's the query upper bound of the OR function, and that is the Grover's algorithm we talked about. And but there's a bit of tricky point here, so we need to talk about Grover's algorithm for unknown m, right? Because yeah. For now, we think about this OR function, and the input string can be anything. We have no promise. And if there is no promise, then we don't really know the number of mark item. So, yeah. So, for the upper bound of the OR function, we need to run Grover algorithm for unknown m. And for unknown m, we know, now it's very tricky, right? But we know that at least it can be done in time order square root n, right? So we know if we are really smart with the binary searching things, then we can do order square root n over m. And then there are several ways to go this order square root n. And let's say a very complicated way is you do the quantum counting with very high precision, the textbook precision. Then that will give you this order square root n Grover algorithm for unknown m. And also we've been talking about so the Grover algorithm has a success rate, sorry, not this, because it's positive. So Grover algorithm has a success probability like this, and we say that, I think, square root n will be maybe square root n will like this, and then you just pick a random point, then you will have like a pretty good probability of getting it correct. Okay? So anyway, there are several ways you can do this order square root n for unknown m. And so that's upper bound, and back to the level of upper bound and lower bound. For lower bound, we just prove it, and we have to review it. And the bottom line is, so the lower bound is quite complicated, as you see. But the bottom line is that the lower bound is omega square root n, right? And so we have a matching upper bound. The upper bound have order square root n, and the lower bound has omega square root n. So we know this OR function has complexity square root n. So we can characterize this quite nicely. It's asymmetrically tight. And I believe that, well, because this is a very clean and simple function, so people have worked this down to even constants. So I think if you try very hard, you can also show those pi over 4 square root n is actually like totally tight up to, I don't know, tied up to additive error, something. But yeah, people have done this very tight. Okay, so that's very cool. We have found the quantum query complexity of one function a lot. And there is another way to phrase our lower bound result. So remember back here, right? So our lower bound, we don't actually count everything. Our lower bound only use the input that are 0 or 1 of them is 1. So our lower bound only use, and obviously we can also run upper bound on those states. So we can also think about this problem with the promise. So if we restrict the number of mark item m to either 0 or 1, or equivalently if we want to toggle all these x in, then that means if we have an extra promise that the Hamming weight of x is either 0 or 1, then we also have upper bound and lower bound, right? So lower bound doesn't change because our lower bound just use this set. Okay? So our lower bound already says that if we have this extra promise, this is hard. And upper bound actually makes it easier. Now we know when we do global search, there is either no item or one mark item. So we can just run global search with one mark item. And yeah. And if we found something, then we know there is something. If we don't find anything, then we know it's no. Okay. So we can also phrase it in terms of this promise problem. And it will also have a tied bound. But I think in terms of competitive theory, people usually talk about this non-promise version because people like total functions where there is no promise on input. And in that case, there will be more structure. Okay. So.
I want to ask a student problem, like why we are so care about tightness?
The tightness? I mean, the first is like, I mean, there can be I mean, there can be practical impact, right? That you want your algorithm to be as basic as possible. And also, so that's like the practical motivation. But in terms of theory, people just want to know the answer. Like, you know what's the best possible you can do, and you just, so whenever there is a gap between some problem, people will work hard to try to match the upper bound and lower bound just because people want to know what's best possible. But if you want more practical applications, then obviously you want your algorithm to be more as efficient as possible, right? So it's kind of like, I guess, in terms of classical computation, there are sorting, right? So people will study all sorts of sorting algorithms and try to get the best possible. I don't remember sorting is like order n, I think. Yeah. Right? Yeah. Okay. Question? Yeah. So that's search problem in terms of return in more complexity theory notation. So that's the quantum query complexity of the OR function. And we say we want to think about other function. And we think OR, and it's pretty natural to think about what's the end function. And we think about it. So now we're starting to be a bit more high level. When I think about OR and end are basically the same function, you are just flipping 0 and 1. And so we say that we argue here, we claim here that the quantum query complexity of end is just same as the OR function because it's very easy to do some reduction between those two. And it's also this theta square root n. Okay? Okay. And yeah. So that's also a quadratic speed up over the classical algorithm. So remember, classical algorithm for all those functions is called R, classical randomized query complexity. OR is theta of n. Now we can, you can pretty easily show yourself. Okay, so that's quadratic speed up. Then you kind of asking yourself, is that everything can have this kind of quadratic speed up, when you run quantum algorithm, and the answer is no. So there is something that with, well, I guess not really no, but almost no. Okay. So there is some function that are very easy that don't have a symplectic speedup, and that's this parity function. Okay. So this parity function is just the parity of all the input bit. So once again we have x1 to x beacon. So it is XOR of x1, x2 to xn. And you can feel that this is a very delicate function, right? So even if you know the parity of x1 to xn minus 1, you still need to query the last bit to know the whole parity. Okay? And okay, so this is a pretty hard function, and classically is order n, and quantally is also very hard. You can show that quantally is also theta order n. And I guess the upper bound is not surprising, so really this omega and lower bound, you need to do some work to show. Yeah. And anyway, so you see that in particularly quantum and classical don't have any separation. But if you if you are really looking up to detail, there is also still a small separation between quantum and classical. That is, you can get a constant factor difference between quantum and the classical, and it's a factor of 2. Okay? And we have actually already seen it. That's just the dual algorithm. Remember, dual algorithm, when we have input being just 2-bit, right? When we input just have 2-bit of x1 and x2, we have the dual algorithm says that with one query we can compute the XOR of x1 and x2, right? So we can just pair everything up with dual algorithm. So we can run dual algorithm to compute x1, x2, x3, and x4, and etc. So that only use over 2 queries, and then you just add up everything else after classically. So that will give you this factor of 2. But that's the most you can do quantally. Okay. Anyway, there is no super constant speed up on this function. So quantum query complexity of all different functions is a very interesting problem to study. And usually so you need to remember we are computing query complexity. And so there is a difference between query complexity and time complexity. So time complexity is the thing we actually want. Right? And so there are some difference between those two, but usually a good query algorithm give you a good time algorithm. So we are pretty justified to study the theory on those query complexity. Okay. Question? I guess also a lower bound of query complexity will always be a lower bound of time complexity. So that's also something. Okay, so let's look at more complicated functions. Oh, sorry. So first, we are titling this as application of a global algorithm, but we already see this, so let's just go through very quick. So once again, global algorithm can be used to speed up and complete problems, because you can just do global search on all the witnesses. Okay. On all the witnesses, or usually the witness is assignment. So maybe the bit string if you are solving 3 set, or like we'll be saying about like a coloring problem, and you can search through all the colors, etc. And but there's a little caveat here. So this don't always give you a speed up over based on classic algorithm, because based on classic algorithm can be smart. For example, when you do traveling sales problem, and so that's a problem where you have a graph, and I believe you want to find the shortest path that goes through everything. And anyway, for training service problem, the number of assignment is like the number of routes through the cities, and that's like n factorial. And but there are classical algorithms that do this in time like order 2 to n. So if you just do global search over those n factorial, then that's square root n to n. So that's actually square root to n, and square root n is bigger than 2. So this is actually worse than the classical algorithm. And anyway, you can do this with smarter way, and that will give you this 1.728 to the n quantum algorithm. But that's still not quite the square root of this, right? Because the square root of that is at 1.414 to the n. And yeah, so that's an interesting question to study. And the algorithm that gets this is actually pretty new. It's 2018. Okay, then it's much slower than I expected. Then finally, we are so we'll probably only have time for this. We are going to solve quantum query complexity for more complicated problem. I guess not quite complexity, we'll only talk about for about. But quantum query algorithms for more complicated problem. So this is the first problem we see. So we're combining our OR and AND. We already know the complexity of those two, right? And OR of AND, because if we do OR of OR, then that's just OR, so that's boring. So we want OR of AND. So what do we mean by OR of AND? It's easier to I guess one way to visualize this is in terms of this bug. So once again, our input is big and B string, right? X is big and B string. And so we think our big N is structured very nicely. So big N is some square form number, so you can read as square root n times square root n. And we put it in this table. So we say OR of AND means we want to compute the end of every row, right? So end of first row is a 0, and end of the second row is a 0, and etc. So we want to compute the end of every row, then we want to compute the OR of those. Okay. So we want to compute this function, which is end first row and second row all the way to end the nth row, and OR of all those results. Okay, so that's OR of different end, order of ends. Okay. And so in terms of this picture, you can also say that the question is there a row that's O1? Because you want to see, is there a 1 somewhere? Okay? And when there is a 1, you know it's the end of everything, so it's O1 here. So say, is there a row that's O1? That's OR of AND function. And you can also think this as kind of a decision tree. So it's OR here and the end. So the OR of square root n different end, and each end is square root n of different input. Right? And you can see that its input is still an NB string because this square has NB numbers. Okay, so what's the quantum query complexity of this question? I guess people want to take a guess. Is this, what's the quantum query complexity? Anyone? Just anything? Square
n over 2.
Square n over 2? Okay. So that's the order square root n, I guess. Yeah, because just the order. So, well, yeah, the answer is almost this. But anyway, let's talk about worst algorithm. So first, classical query complexity is pretty easy to see. This is omega bigger, so let's skip that. And for the quantum query complexity, okay, let's jump to the answer. So the answer is, actually, I think you are correct. So the answer is order square root n, okay? But it requires a completely more complicated algorithm. But so here we will see that you can do square root n log n with easier algorithm. Okay. Okay, we have 5 minutes. But anyway, so let's run a very dumb algorithm first. So quantum algorithm number 1 that give you n to the 3/4. So what you do is you run Grover search algorithm on each row. So all of those end, you just run Grover's algorithm, and you record the result. So this is pretty simple. So each row has square root n items, and you run Grover algorithm, so you only need the square root of those numbers, so that's n to the 1/4 number query you need to do. Okay. And but then now there is some subtle thing you need to take off. That is the error of Grover's algorithm. Okay. So because there are square root n rows, right? So you want that none of those has any error, right? Because you want that the probability of they being all correct is pretty high. So the error probability of each row should be smaller than 1/n, right? So if your error probability is 1/n, then the total error probability is like 1/e, it's constant. And so if you want this 1/n error, then you actually need to amplify your Grover search a bit of time. And so you need to run things log n times. Okay. So the number query here is actually n to the 1/4 times log n. And then this is dumb algorithm, so you run every row with Grover algorithm. Then you just use classical computation to compute the order of everything. And so the classical computation is order square root n time, and the number of Grover you need to run is n to the 1/4 times the square times log n. This is each row, and there are square root n rows. So the total number, and you see this is lower order, so let's just ignore that. And so the total number of query is n to the 3/4 times log n. Okay. So that's a dumb algorithm. And the smarter algorithm is that, 3 minutes. So the smarter algorithm is that after you run the Grover algorithm for each row, you run another Grover algorithm over all the rows. So this order. And so you can run Grover's algorithms recursively. Okay? And I guess we don't write down the details, but the way to think about this is that you can run a Grover algorithm for computing this, right? And there's a quantum algorithm. And you can just think that quantum algorithm as an oracle that you can feed into another quantum algorithm. So think about run Grover algorithm, and with enough precision, you are about doing this. You are running an algorithm that can do this, right? So you will feed the algorithm ith row, and this algorithm will take n to the 1/4 query, n to the 1/4 times log n queries, and so you feed this algorithm some row index I, and it should tell you -1 to the end of the ith row I. And you think about you have this query, then you can feed this query to another Grover's algorithm over all the I, and you can find the order of all those sub-algorithms. And so, okay, going over time a little bit, but then you can calculate the total runtime. Then the auto algorithm is cover over square root n items, so it needs to take this many iterations of the auto algorithm, and each iteration of the auto algorithm, each query of auto algorithm is actually the inner algorithm, and so this thing, right? Each query of this thing is so actually do this. Each query of this algorithm need to be run that many query actually. So you multiply everything through, then the total query is square root n times log n. Okay. So you see we also have a quadratic CBAP over the classic algorithm, but we have this weird log n factor because of error. And we'll not quite see, but we'll argue next time that you can get rid of this log n factor. Okay, any question? Otherwise, yeah, we'll talk more about those application of algorithm on Thursday. And also, we are almost end of semester, so I think we don't have much class left. So we will have our final week, and there are one more week between this week and the final, right? And the next Monday is a holiday, so we have this Thursday and the next Thursday. Okay. And the next Thursday, I'm not sure. I think it's a little weird. Do we want to have class on final week? I don't know, maybe we'll decide on Thursday. We'll think about the final review. Okay. Good. Let's have see you on Thursday.有问题吗？
就是关于前面那个都放这里，有个地方我觉得就是有点小疑问。前面有讲说
是课本的 OK，
对课本，然后就是前面有讲就是它这一项就是 cos tan 的地方，它是一个我的 x 对于我这个 psi k 的那一级。然后我想说，就是前面不是有提过说，就是说那个我可能我的那一级我要考虑说，我可能有几个元素是要被找到的。如果我可能就是对自己那一级之后会有一个 m 倍这样子。
为什么有 m 倍？等一下什么东西？我不太懂你说的 m 倍。
没有，就我们前面可能讲那个 sin 二分之西塔的时候，我们讲说它是我一个，就是我阿法跟贝塔嘛，然后我贝塔对我 sin。
可是这里没有阿法跟贝塔。
对，就是我一直讲说，就是
这里 psi k 是任意的东西，
所以这里 psi k
是可以是任何东西，但是它不管是什么，这个加起来都要是1嘛。因为这里不是说我们在跑 global algorithm， 这里是我们跑任何的 algorithm。它都应该有这个 lower bound，
所以不可以用，就是可能就是前面那个 algorithm 的。
但是也要对嘛，不管你放什么都应该要对。但是这里你会发现这个其实 independent of psi k 的嘛，就是因为这个东西就是不管怎样，你说 x 加起来它都等于1，
对，
我就已经把它绑住了。
所以说我们不可以就可能把 psi k 换成就是可能 n 倍的 x 这样子。
n 倍的 x 是什么意思 ？psi k 要是 normalized 的。所以不管你怎么放，我都不觉得可以超过1。你想的psi k是长什么样子？
我以为就是说可能就是就是可能就是一样可以跟前面一样把它画成2个轴，然后就是可能把2个轴的线性点的 superposition 这样，就可能某一个倍数关系的相加。
你写写看。
没有啊，就是那个。